This is lecture 43 and we are continuing the proof of Krull's theorem. So this was from the last lecture, Rm noetherian, M finitely generated, local, then Sm, which is the length of a system of parameters, equals delta M, which is the degree of a Hilbert-Samuel polynomial, equals dimension M, where Krull dimension is defined as this. And in the proof, we were going to show the three inequalities going in a circle. The first one we had done in the previous lecture. This one we established in the last lecture, and now we will prove this final part. Okay, so this is proof of theorem continued. Okay, so we want to show that. Sm is less than or equal to dimension of M. Okay. So now, because we know it's a finite number, we can induct and prove the statement. So induct on dimension. If dimension of M is 0, then it says that M has finite length. Dimension of M 0 means that annihilator of M is M primary, and therefore dimension of this is finite. Okay, so in other words, so S of M is 0. In other words, we don't need any x's to make it so that the quotient is finite length. So no need of any x's. The system of no need of any system of parameters. It's already finite length. Parameters. Okay. So now let's assume dimension is positive. Assume dimension is positive, and assume that it is true for all modules of smaller dimension. Okay. Okay. So now let's take let P be in. Okay. Let P be a minimal a minimal prime of M. Then since dimension of M is positive, P cannot be the maximal ideal. So we can pick an x, which is just to emphasize, we need to pick such x so that it actually, when you take M mod xm, we get some non-zero module. Okay, because if you take just any x outside P, it could be an invertible element, and if you do M mod xm where x is an invertible element, we would just get 0. Okay, so the reason to choose is we want M mod xm to be non-zero, and we can actually do some induction. Okay. Now let's look at, so suppose y2 through ys is so not to y. Okay, okay. So let T be equal to S of the quotient M mod xm. Okay. What does that say? It says that there exists some y1 through ys inside the maximal ideal such that M mod xm plus y1 through ys times M has finite length. Okay. But sorry, y1 t, not s, t. Okay. So this now means that S of M cannot be longer than this, which is t plus 1. Okay, this is S of M mod xm plus 1. Okay. Okay. So, but what about this number? Okay. Now we need to ensure that. But if you kill an, what about dimension of M mod xm? On the other hand, dimension of M mod xm is strictly less than dimension of M, because if you choose a prime ideal, this avoids a prime ideal below. Okay. Sorry, I wrote prime ideal. Okay, sorry, let's choose a x properly. This is just for any. Okay. Let's choose an x properly. Okay. So let P1 through PR be all the minimal primes such that dimension of M equals dimension of R mod Pi. Remember, the dimension of a module is the maximum of dimension of R mod P as P runs over the minimal primes. Among them, some of them are equality and some of them might be smaller. So just pick the ones that have equality. Don't care about anything else. This is how we worked out in the previous example. We wanted to pick the start of a system of parameters by avoiding primes that determine dimension. Okay, so sorry, I had not picked that thing here at this stage. We need to pick that way. Okay, by prime avoidance, okay, there exists an X inside M, but not in the union of these PIs. This is what prime avoidance said. Given if an ideal, I mean, you don't need maximal ideal here. If an ideal is not in the union of prime ideals, then the ideal is other way around. If the ideal is not in a collection of finitely many prime ideals, in any one of them, then it's not there in the union. Okay. And there are strengthening of this. We don't need all of them to be prime, which you must, okay, which you should have done the exercises. So, okay, so there exists an M with this property. Now for such an X, dimension of M mod xm is strictly less than dimension of M. Okay, that is because the annihilate, I mean, if you need a prime ideal which contains X and the annihilator of this, it cannot be one of these, okay, because none of these contain X. So therefore, any chain which goes from annihilator of this module can be lengthened by at least by 1 to get a chain inside a chain containing annihilator of this. So this dimension is strictly less. Okay, so now therefore induction applies for M mod xm, and so now let's put these things together. Sm is less than or equal to Sm mod xm plus 1. Sm is less than or equal to Sm mod xm plus 1. By induction, this is less than or equal to dim M mod xm plus 1. And because of this condition, this is less than or equal to dim M, which is what we wanted to prove. Okay. So this proves the theorem, and now we want to draw some corollaries of this theorem from One of them is called. Okay. So remember, we have to do all these things to understand the dimension theory of noetherian rings. We got motivated into this because we wanted to understand what is the dimension of polynomial ring over a variable, or in finitely many variables over a field. Okay, we believe that it should be. It looks like it should be the number of variables, but we need proper understanding of Krul dimension to prove that statement. And this is a much more general, works in local rings, etc. But we will need to use these things to go prove that, and needs a little bit more steps to finish that. Okay. So now let's draw an important corollary of this called Krull's principal ideal theorem. Okay. So R noetherian, X inside R, P prime ideal containing x, sorry, not containing, prime ideal that is minimal over x, okay, over the ideal generated by x, then height of P is less than or equal to 1. Okay. I mean, maybe this is a believable statement that if you okay, but it's not, I mean, at the generality of Noetherian rings, this needs a proof. Okay. So the way we will prove it is we will just derive it as an immediate corollary of the dimension theorem that we proved earlier. There are other proofs. One can prove it more directly without doing that much work, but some work has to be done. This is not a very simple observation. It's not an immediate observation from other things. And in fact, it is false for non-Noetherian rings. So one has to use something, I mean, something about Noetherian rings in the proof. Okay. So now let's proof is, I mean, after we have done that theorem, this proof is very straightforward. So what we need to show is that we want to show that dimension of R localized at P is less than or equal to 1. Okay. Notice that x over 1, the ideal generated by x over 1 in the ring R mod P is PRP primary, because there is no, in that local ring there is nothing between the, okay, that's because the radical of this is PR, okay, maybe let me just, okay, in that local ring there is nothing between this, there is no prime ideal between this ideal and that maximal ideal. So this is radical of x over 1 RP is PRP. There are no other prime ideals between these two ideals. This is minimal, and use the fact that PRP is maximal in RP. Okay, so therefore anything that is, so it's P primary. Okay, so this now implies that S of R localized at P is less than or equal to 1. But we know that S is same as dimension. Now this is equal to height. Okay. So this is, so as I mentioned, there are other proofs of this theorem. One such proof, without going to the Krull's dimension theorem, is given in Eisenberg's commutative algebra book. Okay. So another proposition, which is also building up from this, we need some property of prime ideals, which we will need to use in polynomial rings. Okay. So R Noetherian P prime ideal n some integer, positive integer, then the following are equivalent. 1. Height of P is less than or equal to n, and 2. P is minimal over an ideal generated by n elements. Okay. What is called principal ideals theorem is just when n equals 1. We need this version to be used. So proof. So assume, so 1 implies 2. 1 implies 2. Okay. 1 says that height of P is less than or equal to n. Okay. So this means that dimension of R mod R localized at P is less than or equal to 1. Choose x1 over s1 through xn over sn, is less than or equal to n, xn over sn, such that the ideal generated by them radical of this is PRP. Okay. So where are these? Xi's are in P and Si's are not in P. There could be units for this purpose. Okay. So this is for all. So in the localization there is such a ideal. This is again using the theorem. So now let I be the ideal in R generated by the x's in that list in R. Okay. Then of course I extended to RP is x1 over s1 to xn over sn RP, because these are anyway units in this ring, so whether they are inside or not, it's immaterial. Okay, one could have written x1 over 1. Okay, so that's okay. Now what is the claim is that P is minimal over I. Okay. By way of contradiction, suppose that assume there exists a prime Q such that I is inside Q and Q is not P. Okay, so P is not minimal over I. Okay. Then this one would imply that RP is inside QRP, but QRP is not PRP. Okay, and that is a contradiction. Okay, so this proves that P must be minimal. So this is, take any system of parameters in the local ring. Okay, so they will be fractions. Just look at the numerators and look at the ideal generated by that, and that is enough. Okay, that would generate, it would be minimal over P. Just maybe I just mark put as a thing. We are not saying that we don't know that height of I equals n or height of P. Remember, we are not saying height of P is n, it's just less than or equal to n. It is possible that there is some P prime which contains I. It is possible that there exists some P prime containing I, but not inside P. Okay, but P prime is not a subset of P. So that once you localize, P prime became the whole ring. Okay, that will, one would not see P prime in the local ring at RP, but there might be some P prime of smaller height. Okay, so there is, okay, so we are not saying anything about height of I. Okay, so now 1 implies 2. 1 implies 2 is that height of P, sorry, this is that we just proved. 2 implies 1. Okay, this is just so P minimal over x1 through xn implies that height of P, which is equal to height of P, which is equal to dimension of R localized at P, which is equal to which is less than or equal to n, because again the same reason, these things form a system of, these things form something M primary, something primary to the maximal ideal is in this local ring, and that cannot be greater than n then. Okay, so this is the end of this. Okay, so one more proposition. So this choice of x, this is the choice of x that we made in the proof. So let P be let x be in the maximal ideal. So this is, maybe I should just say Rm, the same notation as a proof, as a theorem, Rm noetherian and M finitely generated, and x inside the maximal ideal, but not in the union of all primes where P is a minimal prime and dimension of R mod P equals dimension of M. So an x with which you can actually cut dimension. So we just observed that, then dimension of M mod xm. So in the proof of the theorem we used that dimension of x M mod xm is strictly less than dimension of M, and that is how we built the induction. Okay? But it is in fact equal to dimension of M minus 1. Okay? That is because if you go back to the idea behind the proof of the theorem, we had to pick such an x. If you want to start constructing a system of parameters, we have to pick such an x. Okay, so this is what we want. Okay, we will use an observation that we already made, which is that this is less than or equal to. So we just prove the other inequality. Okay, so proof. We already saw that dimension of M mod xm is less than dimension of M. Okay, that is we used in the proof of the main theorem. Okay, so we just have to prove that dimension of M is less than or equal to this plus 1. Okay, so let x2 through xs be a system of parameters for M mod xm. Okay. So this now means that dimension of M mod xm, so this is where we are using the theorem, is equal to s minus 1. There are s minus 1 elements here, note. Okay, is equal to s minus 1. Now if we choose therefore M mod x2 through xs M is finite length, length over R of this is finite, which implies that S of M is less than or equal to S plus 1. Okay, but this is by the theorem dimension of M, and this okay, and this is S plus 1, sorry, S of M is less than or equal to S, sorry, there are only S elements here, is less than or equal to S, and S is equal to dimension of X plus 1, dimension of M mod xm plus 1, which is what we wanted to prove. Dimension is less than this, and we already proved the other inequality, so this proves. Okay, so this is a statement that is not, I mean, that is sort of, that is not counterintuitive in the sense that if you choose some element, in fact most elements, then when you go modulo that, the dimension will go down. Okay, so you can think of it as geometrically, one can think of it as if you have some z of I, then if you impose one more condition, and if that condition is sort of independent, then the size of z of I will come down. Remember, dimension of M or it's a subset of spec, and that is, one can analogously think of it as z of I for some ideal. Okay, so as we kill more and more equations, the solution set will come down, and if you choose at each stage, if you choose a general enough equation, the solution set's dimension, whatever it means, comes down one at a time. So that is what this theorem is, this proposition is saying. But although it is not counterintuitive, it still needed some amount of work to prove that statement. So this time I chose a different field, a very big field with 32,749. This is the prime number. This is the largest prime number that Macaulay 2 handles, or maybe, sorry, I don't know what the latest version of the largest prime number is bigger, but for some time this used to be the largest prime number. So this is some large enough field, and I will explain why it's necessary to choose a large enough field. Polynomial ring in 2 variables. And here is an equation that we saw. We did our saturation example by hand, meaning with the help of Macaulay with this thing, okay, xz minus y square and x cube minus yz. And we know already that it had, we had identified these minimal primes. Okay, so we had, okay, but if you go back a few lectures ago. But one part was easy, that we observed a minimal xy is a prime, x comma y is a prime, which contains this. And we also already observed that anything that, in that lecture we already observed that anything that's not this prime minimal must contain x and y. Okay, so these two are the only minimal primes. And we also proved that this is the kernel of a map from x, y, z to k t cube t4 t5. So this is also a prime. Okay, so this is, but anyway, we just, in this case I just asked Macaulay to calculate this. Okay, let's now we would like to find a system of parameters. But the point of this example is it's actually not at all difficult, okay, to find. If you choose any linear homogeneous polynomial not inside xy, okay, then we will get the first element in a system of parameters, because of course we cannot choose anything inside xy. And okay, and I chose linear because, see, in this polynomial, this prime does not contain any linear homogeneous polynomials. Okay, in homogeneous, we'll have to check a little bit. I mean, it will not contain, but we'll have to check it with a little bit more difficulty. Okay, linear homogeneous, just by looking at these terms, it's okay. This is already inside the square of the ideal x, y, z. And hence it cannot contain anything which is linear, which needs to involve x, y, and z, linear terms in x, y, and z, right? So that's okay. So this, okay. So for example, we could choose z. Let's kill z and then ask for the ideal generated by the minimal primes. We just get z, y square, and x cube. Okay. Let's check here. So if you, sorry. Here, if you kill z, we get a y square. If you kill z, we will get an x cube, and then there is a z. Okay, so that explains this thing. So I plus z has only r mod I plus z has finite length. So therefore, we just need, so the dimension of this ring. Okay, again, when we say dimension of this ring, we mean dimension of this ring localized at the homogeneous maximal ideal x comma y comma z. We don't need to worry about homogeneity in this problem, but at that the maximal ideal generated by the variables. Okay, it's z is a system of parameters for that. Sorry, it's not x r mod y that is of finite length, but r mod I plus z, which is of finite length. Okay, so in general, if we ask for a general linear polynomial in these sort of situations, it will not be in any finite collection of ideals. So this goes back to prime avoidance theorem, and this was an exercise. If the field is large enough, okay, so typically large enough means infinite. I mean, for sure it will work in infinite fields. In this particular case, this 32,749 was also a large enough characteristic, that just z. So we can just look at this thing here. I take a random element of degree 1 in R. So I got x plus this plus z. So the point is that a random element, most likely, of course, we cannot, if we ask for random element, Macaulay generates it through some random number generator. There are no true random number generators. These are all, so it may so end up that the random element does not involve z, and then we will know it won't work. But if you do random, if you run this command enough number of times, then most of those times you will get with an element which involves z, And in this particular example, as soon as this linear polynomial involves z, that would be enough as a system of parameters. Okay, so that's the thing. So this is a typical thing that one does in Macaulay, that if you just work, if you do this, if you want to identify a system of parameters or something, or if you want to find a general polynomial, we would just run the random command enough times, and whatever is true for general will hopefully be true most of the times in this running of random command. Okay, and just because it's not immediate from here that this ideal is just by looking at this is not immediate that this ideal is m primary, primary to the ideal generated by the variables. So we just ask for the lead terms in some Grosvenor base thing, and we get x, y square and z to the 4. So this is finite length. So that's okay. So in the next lecture we will use these ideas. We will use not the example but the Krull principal ideal theorem to and the characterization of height in terms of being minimal over some number of elements. We'll use that to prove that for a noetherian ring R, dimension of Rx is 1 plus the dimension of R.